So in French, it would be even better, because in French, cart is an embedded graph, a graph embedded into a surface, and then counting cards becomes in French even closer to what we're doing. But Seryoja, I already hear your voice. Can I start?
Yeah, you're welcome, and thanks to Anton for agreeing to give us a series of lectures on.
Thank you very much for the invitation. So I'm happy to tell these several counting tales. And today I would be counting square tile surfaces. The next lecture I will tell how Maria Mirz, and not only, today I would be counting metric ribbon graphs and then square tile surfaces. The next time I will tell how Mariam Mirzahani counted multi-curves and simple closed multi-geodesics, and will show that actually there is surprisingly close relation between counting square tile surfaces and hyperbolic multi-geodesics. And also the next time we'll discuss what one should expect from a typical square tile surface of large genus, or a typical multi-geodesic, hyperbolic multi-geodesic on a hyperbolic surface of large genus. And the very last lecture, the third one, is the sort of a fun one. It's applications to count of meanders. And I will count meanders not only on surfaces of genus Z, well, not only the usual meanders in a plane or in a sphere, I will count meanders on arbitrary surfaces. So this is the plan for the 3 lectures, and the plan for today's lecture is to count square tile surfaces. And before counting square tile surfaces, let me recall how one can count metric ribbon graphs. And before passing to metric ribbon graphs, let me tell about the main actor of this count. So I will need Witten-Concevic correlators. Witten-Concevic correlators, well, they appeared at this seminar many times, so I will just very briefly recall where do they come from. The moduli space MGN has, and its Deligne-Mumford compactification, has plenty of excellent, very interesting geometric structures. In particular, since we're considering complex curves of genus G with n distinct mark points, and these mark points are numbered, we can consider a tangent plane to their point number, say, 3. Well, since algebraic geometers prefer to consider these Riemann surfaces as complex curves, so we have a tangent line at the point number 3, and by some mainly historical reasons, they prefer to consider cotangent line. Now, when you start deforming your surface and deforming the location of points, you get a family of lines, and a family of lines parameterized by points of MGM. It is sort of reasonable to expect, and it really happens, that this family of lines has a structure of a holomorphic line bundle. And we have as many holomorphic line bundles as marked points. So for every marked point, we have its own holomorphic line bundle, which is denoted Li and called tautological bundle. And as any holomorphic line bundle, it has first Chern class, and we get n Chern classes. Now, the dimension of the base space of MGM is 3G minus 3 plus n. So all these classes have rank 2, real rank 2. So if we take product of them, where we take first class in the power d1, etc., the nth class in the power dn, and we arrange the powers in such way that the total product is a class which has dimension of the base, that we can integrate this already the top class, we can integrate it over the base. Now, if the base would be complex manifold, we would get just an integer number. Here, the base is a complex orbifold, so we get rational number. And for every partition of the number 3g minus 3 plus n, which is complex dimension of the base, so for every integer partition into sum of n non-negative integers d1, etc., dn, we get a rational number, which is called the Witten-Concevic correlator, and algebraic geometry is denoted like this, and Witten denoted it symbolically like this. But what is important here is basically that to every partition of 3g minus 3 plus n, we have a geometric way to associate the rational number. Now, the famous Witten's conjecture claims that these numbers satisfy certain recurrence relations. And originally, all these numbers were, for all g and n, were wrapped into one generating function. And the recurrence relations were encoded by certain differential equations which were satisfied by this generating function. Now, the first proof of Witten's conjecture was obtained by Concevic. Then there were alternative conceptually different proofs due to Akunkov and Pandaripande, to Mariam Mirzahani, to Maxim Kazaryan and Sergei Landau, and there are other proofs. So by now there are many proofs. And ever since, these intersection numbers are quite famous, and they really pop up in quite different problems. Now, one of the ways to write these recurrent relations, so we have plenty of rational numbers and they're not independent, they are all related. One of the ways is not to write differential equations on generating function, but to write straightforwardly relations between numbers directly. So basically, all the numbers are defined by the two initial ones, which are in the first line of the slide. And there are these three groups of recurrence relations where the main one, the sort of the general one, is this one. And I showed mainly to convince you that it is complicated. Because, and that in reality, when you want to compute these intersection numbers, yes, so this shows that there is an algorithm and the relations are very explicit. But the trouble is that when you start computing them on computer, then the complexity becomes very high very soon. Because, for example, in this term, which is the bottom line, you have to split your partition in all possible ways into two partitions. And the sum becomes gigantic for already relatively small values of g and n. So the main trouble here is n, not the genus, but when n starts to grow, it becomes really very difficult to compute them and the computation becomes slow. So there is some issue here. First result, which I would like to advertise, is the following theorem of Agarwal, which is very recent. And you can think of this theorem as sort of a multivariate analog of Stirling formula. When you need to compute n factorial, then when n is, say, up to 6 or 7, you know the values by heart. And here the recurrence is particularly simple. But still, when you need to know, well, when you need to use factorial of, say, 100, you do not use the recurrent relations. You use Stirling formula. You use approximation. So here, this theorem of Agarwal gives a uniformly good approximation of all these intersection numbers when genus is sufficiently large and when the number n is not too large compared to genus. So this theorem states that you consider all these intersection numbers at once. So in other words, you suppose that genus G is sufficiently large and N is not too large compared to genus, meaning that it's so smaller than square root of, considerably smaller than square root of G. And then simultaneously for all possible partitions of 3G minus 3 plus N, you get this approximation where the error term is uniformly small for all this gigantic number of partitions. So I will need this theorem of Agarwal soon.
Sorry, Anton.
Yes?
Can you be more precise? Because as G goes to infinity, we are unable to fix D's. So that the sum is 3G minus 3 plus N. So what is, how this statement can be made precise?
So I think that the answer to your question is in this world uniformly. So you consider, so choose, say, some growth rate of N. For example, square root of G times some function of G which tends to 0, some explicit function. Then, and let G tend to infinity. Then for any fixed G, you have finite number of partitions. And I'm claiming that you take all these partitions, you evaluate this quantity, you measure what is the worst error term which you get over all partitions like this. And I claim, well, or rather Agarwal, well, we conjectured and Agarwal proved that this error term tends to 0 even if you take as epsilon the worst error term which you get over all possible partitions which satisfy this relation. Did I answer your question or not yet?
Yeah, in a sense, but what can I expect? The worst case will be if all the D's are the same, or if all of them but one are ones, and the last one...
I see. This is, so you are basically, the question is, what are the partitions for which this error term is the worst?
Yeah, exactly.
Okay. The appropriate, so what I will answer is not a rigorous statement, it's experimental fact and a conjecture. And this conjecture belongs to Vансаном Делекруа. So he tested different partitions and he guessed on which partitions this error term attains minimum and maximum. The table is relatively tricky, but not very tricky. And the main point is the following. So if you allow partitions with small values of D, say if you allow values 0, this is one story. So, and there, I don't remember by heart in what, so there are several ingredients because there is also dependence on N, and depending on N, one partition gains or another, but morally, the answer is you have to consider separately partitions which contain 0. And probably I have to come back to this story because for 0, you have the string relations, partitions containing 0. They are sort of partitions apart. And for them, you have one answer. Now, for those partitions where entry 0 is not involved, but entry 1 is involved, you have the other answer. Now, if both entries 0 and 1 are forbidden, and you consider only partitions where every entry is equal to at least 2, there is the third answer, and every time your error term becomes much better than before. And I have somewhere a file of Vincent with explicit conjecture. I don't remember it by heart, but morally it's like this. And I really believe in this conjecture, it was checked quite seriously. So it can, so this theorem can be pushed to a stronger form in many directions. For example, yes, it is possible to indicate explicitly what is the partition for which the error term attains minimum and maximum. It is possible also to go so possible. I'm saying that it's conceivable. It's all what I'm saying is sort of experiments and conjectures, but it looks like you can go beyond this square root of g, but then you have to modify this formula. But you can modify, so you have to modify this factor. It wouldn't be 1 anymore, but it looks like we have a reasonable guess of how it would behave beyond square root of g. As you see, this is a very recent theorem, and we just didn't have enough time to play with this.
Okay, I caught it. If the case when all the d's are at least 2 is distinguished in this or that sense, then it makes sense. Thanks.
Also, I should say that the story is actively developing because there is a recent paper of Gur and I forgot the name of his collaborator with some polynomiality conjectures. So I don't want to go, so it could be a subject of a separate discussion for several hours, but there are plenty of things where this can be improved and very considerably. And I think that in the forthcoming, I don't know, 10 years, it would be improved considerably, no matter whether we would work on it or other people would work. So it's just the beginning of a beautiful story. Okay, so this is this large genus asymptotics. And now I will, so I'm coming back to this individual correlators. And let me fix G and N. Then there is finite number of them, which are parameterized by partitions of 3g minus 3 plus n into n non-negative integers. And as always, when you have a huge pack of numbers, it is reasonable to wrap them into a generating function. And now, since there are only finite number of them, it would be, our generating function would be a generating polynomial. So I will introduce formal parameters b1, etc., bn, and I will encode the entries of our partition, which are responsible for the intersection number, for this correlator. I will encode by multiplying the corresponding correlator by b1 power 2d1, b2 power 2d2, etc., up to bn power 2dn. Up to now, it's just a formal operation. I introduced formal variables b1, etc., bn, and I multiplied all these correlators by these monomials in letters b. And by technical reasons, it would be convenient to memorize these correlators with the weight which is here in front of the integral. And then I sum up all this, these monomials with coefficients which correspond to intersection numbers, and I get a huge polynomial which remembers everything about all intersection numbers, because picking up appropriate monomial, I have this coefficient in front of this monomial, and I have the corresponding intersection number. Now, I said that it's purely formal operation, but actually one of the reasons why this choice of weights is really reasonable is that, is that actually this polynomial has geometric meaning. Up to the factor which is power of 2 and which is just power of 2 depending on g and n, this very explicit power of 2, the polynomial which I constructed is responsible for the Weil-Petersson volume of the moduli space of bordered Riemann surfaces. So you consider hyperbolic surfaces with boundary. You assume that your boundary is geodesic, so you do not chop somehow, you chop by geodesics. And you impose lengths b1, etc., bn to this n boundary components of your hyperbolic surfaces of genus G. You get a moduli space, and Mirzahani proved that the Weil-Petersson volume of this moduli space, which is generalization of the usual moduli space of hyperbolic surfaces, is exactly this polynomial with coefficients which depend on intersection numbers. So it has this hidden geometric meaning. I will need these polynomials for other story. But before I'm passing to this other story, let me tell slightly in advance how I will come back to numbers. So at some point, I will return from polynomials to numbers, and I will get rid of these monomials in the following way. Instead of having all these monomials in my variables b, to each monomial, I will associate the following number. So I have n variables, b1, etc., bn, and to every monomial in b's, I will associate the number which records the power of each variable and takes factorial of this power, then multiplies by this funny zeta, where you take the corresponding power and shift by 1, and then you take product with respect to all variables from 1 to n. So to every monomial, we associated this funny number, and then we extend this by linearity to all polynomials, to all homogeneous polynomials. So we'll need this operator in 1 or 2 minutes. And now let me state the counting problem. So the first counting problem of this lecture, which was solved quite a while ago, is the following counting problem. What you see here in the picture is a ribbon graph. And a ribbon graph, you can imagine it as a graph to which you glued a ribbon. So you take a sort of a tubular neighborhood of a graph. And so topologically, it's just a surface with boundary. It has some genus. It has a certain number of boundary components. I will always work with oriented surfaces. And now I will impose some additional structure. I will assume that my core graph, the true graph, which is constructed from true edges, so that it's a metric graph, that all the edges have...
Sorry, Anton, just to be precise, are you talking about oriented graphs or oriented surfaces or orientable surfaces?
Orientable.
Orientable, okay.
Mm-hmm. I certainly orientable. I think that I do not see directly orientation. So I think that just orientable. So now I assume that all the edges have length. And moreover, I assume that this length are positive integers. So as soon as every edge is attributed some length, then we get length for boundary components also, because when we have a boundary component which follows the edge, this edge contributes its length to the length of boundary component. Then if our boundary component follows the next edge also contributes its length to the boundary component, and so on. So the length of every boundary component is the sum of the length of edges which it follows. And now I can state the counting problem. Fix the genus of the surface which corresponds to the ribbon graph. Fix the number of components. And let's count how many, and fix the lengths of boundary components. When you fix the length of the boundary component, it does not mean that you know the length of individual edges. Everything depends on topology of the surface, and you can have a lot of freedom. So now the question is, how many ribbon graphs you can construct when you impose to the ribbon graph to have genus G, to have n boundary components, and when you impose to these boundary components to have lengths B1, etc., Bn. And the solution to this counting problem is exactly this Concevic polynomial, which I showed at the previous slide. So this is another geometric meaning of this polynomial. So in the setting in which I need this theorem, I need only asymptotics when all these b's are large. But this original statement was somehow specified by Norbury in 2010, and he proved that this statement is not only asymptotic, it's exact statement for all b's, except that you have to consider this n on the right not as polynomial but as quasi-polynomial. So somehow when the variables b do not satisfy some parity conditions, the value is just 0. But so I don't need this statement in this most is in the strongest form due to Norbury. I will need it only assuming that all these b's are large, and this polynomial ngn, which we constructed, is responsible now for the count of metric ribbon graphs. So when we count metric ribbon graphs of genus G with n boundary components of length B1, etc., Pn, the problem is solvable, and the solution is given by this polynomial where coefficients are expressed in terms of Witten-Concevic correlators, the intersection numbers of psi-classes. Okay, so this is the end of the first story which I wanted to tell today. And this is already a beautiful problem. And now I want to pass to count of square tile surfaces. So square tile surface is the surface which you see on the right picture. And so here on the right, to make the picture simpler, I constructed a very peculiar and very special square tile surface. So I just took square tiled paper and chopped 2 copies of this polygon which you see from this paper. And then I took these 2 copies and identified by the common boundary, which follows the boundaries of squares. And I got a pillow, so I got a topological sphere, and this topological sphere is obtained by attaching squares to each other, where I attach sides to sides, edges to edges. Now, a more realistic model of a square tile surface is here. So this is, I can show it like here. So it is really square tile sphere. Now, it is even better than square tile because you can probably see that I'm using not the squares but parallelograms, and it is more realistic model because I want to consider only square-tiled surfaces where all the squares are polarized. I have two vertical edges, two horizontal edges, and when I'm attaching squares to squares, I attach only vertical only to vertical and horizontal only to horizontal. And now the problem which I want to solve is the following. So you see that there are many points where, many vertices where there are four adjacent squares, and that's just the regular points. And also there are sort of special points. There are points where, like at this point, we have only two adjacent squares, and they are really special for me, and I want to count them separately. And I will memorize how many points like this do I have. And also there are points where we have 6 adjacent squares, 8 adjacent squares, and so on. So anticipating, so I will tell about it slightly later, but actually one of the interpretations of a square-tiled surface like this, this is a meromorphic quadratic differential, and points where you have 6, 8, and so on adjacent squares are zeros of this differential. And points where you have exactly 2 adjacent squares are simple poles of the quadratic differential. So I will memorize the number of simple poles. I will memorize the genus, and that's my parameters g and n. And now the question is the following. So I fix these parameters g and n, and I ask how many square-tiled surfaces can one construct if you have at most huge amount n and capital squares, and if you impose to the resulting square-tiled surfaces to be connected and to have genus g, and to have exactly n conical points with cone angle pi, like these corners here. So that's the problem which I want to solve. And more concretely, one can really easily check that the growth with respect to number of squares which we can use is polynomial, and the degree of the polynomial is the dimension of the corresponding moduli space of quadratic differentials, which is easily expressible in terms of g and n. Now, what is much more somewhat interesting is the coefficient in front of this polynomial asymptotics. That's the main object of study. But I'm somehow jumping ahead. Let me come back to this counting problem. And right now, the main issue is to convince you that this problem is basically already, conceptually, is already solved using this count of metric ribbon graphs. Well, to convince you that the two problems are related, and also to prepare something for the lecture in a week to relate the square-tiled surfaces with multi-curves, let me associate to every square-tiled surface a couple of objects. First object is the following. I can associate to any square-tiled surface a topological surface with n mark points. So I mark all the corners, all the points where we have only 2 adjacent squares by little corners like here. So it's even better to imagine that we have sort of hyperbolic surface and that we have cusps at all these points. So as soon as I have a point like this, where there are only 2 squares which are adjacent, I create a cusp which pushes out of this point. I don't want to memorize the location of other singularities, but I want to memorize the following thing. My square-tiled surface has natural decomposition into cylinders, and in every cylinder, so here in my picture, the cylinders are expressed by different shades of different intensities of this very gray part of the surface is one cylinder. And if I take any point of this, of two bottom rows of squares, and if I will consider a horizontal line passing through through a point like this, I will get a circle which is parallel to this red circle and which would have exactly the same length. This would be for all the points of this gray cylinder. But when I cross this critical level, the cylinder...
Sorry, Anton.
Yeah?
What do you mean by calling this gray part a cylinder?
That if you take a complement of the surface, probably I have to, so in this picture, I colored in blue all critical horizontal levels.
Mm-hmm.
So we have this critical horizontal level, then one here, then one here. So now I'm coming back to this picture. So let me withdraw from my square tile surface all critical horizontal levels. I'm calling a level horizontal level critical if it contains any singular point, any point with cone angle different from 2 pi.
Okay.
I claim that the surface, what would remain, would be a union of flat cylinders. For example, so here I have to remove this bottom line. It will open up, and the boundary would become just a circle which would be parallel to this red circle and which would have the very same length. I take a cylinder, and then at the bottom I take two diameter points and identify two arcs of a circle by gluing them together. I will let me make an illustration, a physical one. Without kidding, I have probably it would be better visible like this. So the bottom part of the picture is like this. I have a true flat cylinder, and now here I create two corners, and this is the bottom of my surface. And also the top parts are exactly the same, except that I have to take it upside down. But if I open up by this part, I will have my horizontal cylinder. So here with this surface, I have cylinder here. Then I have another cylinder here. I have cylinder here.
Sorry, we do not see your pictures.
Oh, really? You don't. I see. Sorry. You see only.
Yeah, exactly.
You see only the. I apologize. Just a second. I will stop. Oh, then you wouldn't see. Anyway, I will show here. I will show on PDF pictures. So I'm claiming that if you cut the surface by this line and open up, and also if you cut the surface by this critical level, then this dark gray thing would become physically a flat cylinder, a true flat cylinder.
Okay, and what is about the upper critical level on the right?
On the right. So here is the bottom of this cylinder. The cylinder is constructed from, well, that's the cylinder. And you have to cut by this line and open it up.
And am I expected to cut also along the circle on the left, which belongs to the same level?
To cut over, oh, you mean this thing?
Yeah.
No, you just, so let's, I see. I'm taking only connected components of critical levels. So I'm taking, so here we really have this critical point and this critical point. And this segment is my critical level. Now, this is a separate connected component which is perfectly regular. I don't need to cut over it.
Okay, now it's more or less clear.
And now I understand the question. So you take all critical points, you make expand this separate recess from these critical points and take the union of, well, and this is the union of critical levels. So in this, yeah, they are drawn in blue on this picture. Okay, so sorry, I somehow, since I'm playing with this decomposition of square tile surfaces into cylinders for more than 20 years, I'm so used to it that please do ask questions somehow. For some things, I assume that they go without saying, and saying is needed. So some questions I really, it's difficult for me to anticipate. Thank you for asking. Okay. So now we discuss this decomposition of the surface into maximal horizontal cylinders.
Yeah, a question from Maxim.
Yes.
Why do you call the associated metric hyperbolic?
This one?
No, on the
here in the main picture, the metric is flat.
Ah.
The picture on the metric on the left surface will be hyperbolic soon. Right now, it's just topological picture, but actually I can tell what is the associated hyperbolic. So I can find a hyperbolic metric in the conformal class of this flat metric. So, and probably it would become even easier if I will show this picture. So I want to associate to our square tile surface also a stable graph, which is on the right, which is formally just the dual graph to this collection of red curves, where the mark points, which are on the left picture, denoted by these horns or cusps, are encoded on the stable graph by these half H's. So there, in terms of square tile surface, the vertices of the stable graph correspond to their critical levels, and the edges encode cylinders. And the entire graph tells you how critical edges are arranged together by cylinders. Now, the notion of stable graph, it's not coincidence. So stable graphs encode stable curves. So they encode boundary classes of mg and bar. And indeed, if you take a surface like this and you pinch all these red curves, then you'll get a stable curve which is encoded by this stable graph. So more geometrically, you can imagine this in the following way. Consider this square tile surface and apply a transformation which makes horizontal distances much shorter and which expands everything vertically. Then we'll get very narrow and very long cylinders with large moduli. And if you consider the associated hyperbolic metric, then basically the waist curves of cylinders would be almost shrinked to points, and we'll get in the limit this stable curve. But this is not, I do not need this geometric interpretation. I'm perfectly fine staying on purely formal level, that to every square tile surface, we associate a collection of red curves, which encode the waist curves of maximal horizontal cylinders. and that the dual graph is this stable graph. Now,
sorry, just
I can finally,
just
yeah.
to be sure. On the left picture, you have horizontal circles. Yeah, red.
On the left, on horizontal what? Saddle?
Circles.
Ah, circle. Yes, I have 4.
Yeah, you have 4 circles. Whether there are horizontal geodesics in your hyperbolic metric, or you do not assume?
So, for any hyperbolic metric which I impose on this left surface, these curves, which take, if you let them contract in the free homotopy to geodesics, they would take the form of geodesics, and you will get this multi-geodesic, and the resulting geodesics would be still not self-intersecting and not pairwise intersecting. So the answer is that for any hyperbolic metric, you can realize these 4 red curves as geodesics, or rather as multi-geodesic.
I asked a different question. I asked whether these geodesics will be horizontal.
Oh, whether they would be? No. No. On the hyperbolic surface, there is no notion of horizontal. So I have a notion of horizontal on my flat surface because of the following. So the holonomy of my metric lives in the group Z over 2Z. So if I make a parallel for for a square tile surface, when I make a parallel transport, and it does not depend on genus 0, whatever. So when I make a parallel transport of a vector on a square tile surface along a closed path, it comes back either in the same direction or in the direction turned by to the opposite direction. There is no holonomy, almost. So the worst thing is that it can get turned upside down. No, I do not see, there is nothing like this for hyperbolic metric, right?
It's true, but when you draw a surface like that, this suggests that there is some distinguished height function, which is not correct, I believe, yeah?
So my picture is purely schematic, and you can consider it as a topological picture.
Okay.
So there is a way to choose a hyperbolic metric which would be sort of reasonable, but basically you can consider this as a topological picture, and any hyperbolic metric with this connection of cusps.
Mm-hmm. Yeah, but and there is no distinguished hyperbolic metric. There is a bunch of hyperbolic metrics with this property.
I see. No, there is a distinguished, or at least a one-parameter family. There is a one-parameter family of distinguished hyperbolic. Well, there is even distinguished hyperbolic metric, because you can consider the hyperbolic metric in the conformal class of the flat metric. There is one. I never tried to think what is special about geodesics in this particular metric. I don't know.
Okay, thanks.
Okay. Now, with all these preliminaries, I can tell you how we'll compute square tile surfaces. Let me first show how to compute square tile tori. Basically, I can cut my square-tiled torus by any horizontal curve passing through vertices of squares, they are all the same. I will open it up and I will get a cylinder, which will have well, the length of this horizontal curve, which would be B. It would have height h. And if I want to glue back torus from a cylinder with parameters b and h, I have to choose some twist phi, which I will use when I identify two boundary components. So I somehow bend my flat cylinder like this, and when I identify two boundary components, I can identify directly, or I can identify by twisting by 1, by 2, etc., up to length b. I do not consider more than b minus 1, because otherwise I can apply bend twist, so I can apply a diffeomorphism, and I reduce to twist parameter to the situation when the twist parameter varies, well, is located between 0 and b. So that means that to compute square-tiled tori, I have to take the following sum. I have to vary b, h, and for every pair b and h, I have b options of twists. And also this bh should be such that the total area, the number of squares, which is the area of the cylinder, which is b times h, is at most n. And so I have to compute sum like this. And so basically, I have a polynomial in one letter b of degree 1, this polynomial b. And from this polynomial, I make this simple-minded manipulations, and I obtain a quadratic asymptotics in the number of squares with a very explicit coefficient. And note that this coefficient is exactly our operator z applied to parameter b. So recall that we had this funny operator z, which associated to any monomial in formal letters b, a number. This is a particular case. Now I can count square-tiled surfaces. And actually, they were supposed to be counted 20 years ago, or even 30 years ago by now, because the work of Concevichu is 92, so they could be counted. Everything was ready to count them many, many years ago, because I will count them in the following way. I will count them, say, for example, here, this is a count in genus 2. In genus 2, when g is equal to 2 and n is equal to 0, so there are no cusps, there are 6 possible stable graphs, which are on the right column in this picture. I will compute contributions of square-tiled surfaces corresponding to each stable graph separately. As soon as I have fixed stable graph, I consider the decomposition of my square-tiled surface corresponding to the stable graph, and probably I have to come back for a second. So as soon as I have a stable graph, I consider the corresponding decomposition of my square-tiled surface. So I decomposed it into ribbon graphs. So each layer, each singular horizontal layer is a ribbon graph. And it's a ribbon graph for which I will use variables b1, etc., for the length of the boundaries. Now I already know how to count ribbon graphs with these parameters b. And the only thing which remains is to join these boundaries by cylinders. I know which boundary component to join with which boundary component, because this is encoded by the structure of the stable graph. And when I join a cylinder, I have this extra parameter twist, which I can use. So I will get an extra factor b, like in this computation of square type tori. So all horizontal parameters are already fixed, and then there are vertical parameters, and there would be a computation similar to this computation of the tori, where we sum over all possible horizontal parameters b, but they would be these vertical parameters h, which are responsible for heights of cylinders involved, by somehow they would be wrapped easily in this computation. And believe me that what will pop out of here is a power of n, which would be easy to compute, and the coefficients would be computed by the funny operator z. So basically in this genus 2 computation, so the polynomials which you see here in this column are polynomials which correspond to the corresponding ribbon graphs. So here there are two components. So there would be two polynomials. So this curve chops the surface into two components of genus 1 with one boundary component of length b1. So we'll have this product of n11 b1 and n11 b1 corresponding to two boundary components. When we glue them by cylinder, there would be extra factor b1, which is responsible for the twist. And now this red and blue factors, red factors are responsible for symmetry of the stable graph, and blue factors take into consideration some effects of parity, which I don't want to discuss, which are sort of technical details. So I'm claiming that as soon as we know how to compute ribbon graphs, the computation of square tile surfaces corresponding to this particular stable graph becomes sort of straightforward. So you write these polynomials, then so the polynomials, recall that polynomials are formally defined in terms of psi classes, so the coefficients depend on psi classes. You compute these psi classes, you get explicit polynomials, then you apply this funny operator z, you get numbers, and the numbers on the right are the contributions of square tile surfaces corresponding to this particular stable graphs, and you sum up and you get asymptotics in their count of square tile surfaces of genus 2. So the general formula is for count of square tile surfaces of genus G with n corners is here on the slide. The only thing which is really important for me is that this is a sum of positive contributions and the sum over all possible stable graphs corresponding to this topology. So the main point is that the problem, we basically reduced the counting problem to a variation of counting problem for metric ribbon graphs, and that we have to use the sum over all possible stable graphs. This is not that important. And so this is the answer. And now I have to, my plan is to explain why.
Sorry, one step back. The weights are the genera of the corresponding vertices, or? So
this weight is this
no, you sum over the weighted graphs.
Yes.
Stable weighted graphs with n legs. What is weighted here?
Like here. So I'm summing.
These are genera, yeah?
That's all possible stable graphs which correspond to surfaces of genus 2 with no mark points. So that's all possible boundary classes for M2.
Yeah, but the vertices of the graphs are weighted with the genera of the components, while the edges are weighted with the parameters b. Yeah,
I see. Yeah, so there you're right. You are right. this stable graphs should be in, so the vertices, so here I have this number 1, which is the genus, absolutely. And yes, to every side we associate this letter B. Yes.
That's what was my question.
Yeah. So I apologize. I was somehow a little bit brief. So the stable graph actually is enhanced with this extra information. To every vertex you associate a non-negative integer, which tells you what is the genus of corresponding, in our interpretation of corresponding ribbon graph. Okay, now now I have to demystify the words Мэйзура-Вич volume of moduli space of abelian differentials, and I have to convince you that this count of square tile surfaces is exactly the count of volume of the moduli space. But first, I have to introduce this moduli space of abelian differentials, or quadratic differentials. So let me first introduce flat surfaces, or rather very flat surfaces. So torus is a very flat surface, and if we glue, so torus can be obtained by gluing opposite sides of a square, and it's very flat because the holonomy of the resulting flat metric on a torus is trivial. You make a parallel transport of any vector over any closed path, and the vector comes back exactly in the same direction. So now let me convince you that they're flat surfaces of genus 2. And to convince you, I will chop the 4 corners of the square, and then I will pretend that I'm gluing a torus from a square. But since I chopped off 4 corners, I will get a torus with a hole. And this hole will have a form of a smaller square. From now on, I will, so already this picture is sort of schematic and topological. Let me turn this hole by 45 degrees, and let me identify 2 more opposite sides. Oops, sorry. I get a torus now with 2 holes, which are isolated. And then when I identify these 2 holes by gluing them together, I get torus with a handle. So in this way, gluing opposite sides of a regular octagon, I get a perfectly flat surface of genus 2. And there is no contradiction with Gauss-Bonnet theorem, because one can easily check that all the corners of the regular octagon are identified into one point, and we have sort of a multi-saddle there. The total cone angle at this point is not 2 pi, it's 6 pi. Now the next, so this was just an example. Now let me convince you that this example can be generalized. So I can consider much more general octagons. So an octagon like here is constructed in the following way. I take more or less a random broken line constructed from 4 vectors, this black one, then red one, then green one, then blue one. And then I start from the very same point, and I construct a new broken line using the same vectors, but I construct a new broken line using another order of vectors. So I first, in this particular case, I first take blue, then green, then red, then black. Since I used the very same vectors as before, I will get to the same point, so I will get an octagon. And as you see, it's an open condition that these 2 broken lines do not intersect, so I can deform my octagon a little bit. And it is constructed in such way that the sides are distributed into pairs of sides, where in every pair, the sides, which are colored by the same color, they're parallel and they have the same length. So I can identify them by parallel translation, as in the previous picture, and I get a flat surface. and it will have the same topology and as before, as in the previous picture. So I get varying independently these factors.
Sorry, and why the topology will be?
Because combinatorics of identification is the same.
Yeah, but you were able to choose a different order of vector.
If you compare it with this one, you can verify that the permutation is 4, 3, 2, 1 as before.
Yeah, that's what I understand, but you were able to choose a different order.
Or if I will choose another permutation, I risk, so I will get to another genus. And so all permutations are grouped into large classes where in every group, permutations bring you to a given stratum. Okay, it's a separate story, but there is operation which is called Rosy induction on permutations, which allows to construct all these classes. Okay, now one more story here is that actually, so I constructed a flat surface. Let's assume that our polygon lives in a complex plane. I want to distinguish between this polygon and polygon turned by 30 degrees. For me, they are different. So I can make parallel translations, but I'm not allowed to turn this thing. I don't want to turn it because I want to use the following structure, extra structure. First, since my polygon is placed now in complex plane, I get complex coordinate on a polygon. And when I identify opposite sides, you can see that this identification in our coordinates is in local coordinates is extremely nice. It's local coordinate z near one side corresponds to coordinate z plus constant near the other side. So our identifications are extremely holomorphic. I get complex structure on the resulting surface. Formally speaking, on the resulting surface, we have to puncture all the corners, but one can check that the complex structure extends nicely to these corners. Also, I can consider form dz. And here I really want to use the fact that my partner is placed into a complex plane after a parallel translation and that rotations are forbidden. So coordinate z is not globally defined after identification of h's. But since the identifications are z equal to another local z plus constant, when we pass to differential, the differentials are the same, and you really get well-defined form dz on the surface. And again, an exercise in complex analysis is to verify that points which come from vertices of the polygon give rise to zeros of this holomorphic one form. So we get a abelian differential. Now, our vectors can be seen in the following way. So if you consider a black vector or red vector not as a vector in R2, but as a complex number, then this complex number is nothing but integral of the form dz over the corresponding side. So these vectors considered as complex numbers are periods of our holomorphic one form, where we consider not only periods with respect to closed curves, but also with respect to paths joining zeros. So basically, we get an element of the first cohomology of our surface relative to collection of zeros with complex coefficients.
Yeah, but here n is just equal to 1 because you have a single zero, yeah?
Yes, in this particular case, I have single zeros, so n is equal to 1, yes. But if you take sort of some random permutations of 55 elements, then you get several zeros. And you can get any collection of zeros as soon as sum of degrees of zeros is equal to 2g minus 2. So you get different kind of strata of holomorphic one forms. So we get natural period coordinates. And in these period coordinates, we also have integer lattice. So instead of considering coefficient C, we can consider coefficient Z plus IZ. Excellent. So we have very rich structure. And also we have the area of the surface. We can proportionally contract the surface or expand the surface so that the area, the flat area of the surface becomes equal to 1. And in terms of our form, it's the integral of omega bar up to a factor I over 2. In terms of periods, this is this quadratic expression in terms of periods. So we have, in this way, we can define a unit ball. We can consider flat surfaces of area at most 1. And now forget about strata and so on. So first, let's consider just all holomorphic forms on curves of genus G. So for each individual complex curve, we have a G-dimensional complex vector space of all possible holomorphic forms. So this modular space of all holomorphic or pairs complex curve holomorphic form, but this is just the total space of a G-dimensional vector bundle over Mg. Of course, here, and we have natural volume form on this total space. Of course, there is no way to compute the volume of this total space. It will be infinite. But now we define sort of the bundle of unit balls in these vector spaces, restricting the area of the surface to at most 1. And this is already still not compact something because the base is not compact, but it has chances to have finite volume, and indeed it has finite volume. So, and the point now is we want to compute this volume. So, coming back to more formal definition, we have the following structures. For every stratum, when we fix the degrees of zeros of our holomorphic 1 forms, and also we fix the number, so we have n zeros of fixed degrees. So we have the following structures. We have local structure of a vector space, which is cohomology. That's our period coordinates. So our strata are modeled on this cohomology. We're lucky because in this cohomology, we have integer lattice in these vector spaces. So this allows, so when we have a vector space, we have already a family of distinguished volume elements defined up to a constant factor. As soon as we have a lattice in a vector space, we have a distinguished volume element. So we take a linear volume element in the vector space such that the fundamental domain of the lattice is normalized to have volume 1. And also, so we have this, the first two structures define a distinguished volume element. And the last thing, a positive homogeneous function, which is the area, the flat area of the associated surface, this integral of omega bar, allows to define an analog of unit sphere or unit ball, or it's rather unit hyperboloid. And theorem of Méйzura-Vich says that the total volume of any stratum defined like this is finite. Now, how to
sorry, can you be more precise where this function comes from?
Oops, this one. So in period coordinates, it's like this. And geometrically, as soon as you have holomorphic 1 form, you can compute the integral of omega bar over the curve, multiply by I over 2. And what you get is nothing but flat area of the corresponding surface. So it's positive. And we use this function to define sort of unit ball. Okay, now I claim that now I'm coming to finally to square-tiled surfaces. I claim that integer points of our lattice, so points which in period coordinates correspond to integer points, when all periods, relative and absolute, live in z plus iz, that surfaces like this are square-tiled. So first, a pictorial proof. So when the lattice points correspond to surfaces where all our vectors, which we constructed, which we use to construct a polygon, when they have a form, when they're integer plus I integer, like in the picture. When you have a surface glued from a polygon like this, then you can make the following operation. Since this is just a pattern and we can rearrange it in the way which is convenient for us, we can chop, for example, this shaded in blue triangle. And since the blue side is glued to blue side, we can put it where it is placed now. Then I will chop another triangle, which is now shaded in yellow. And since the green side is glued to green side, I can put it at top and up. Now my square tiling is already completely visible. So this is sort of naive pictorial proof. A more formal one is the following one. So we get a square tiled surface. The formal one is the following. When all the periods of my holomorphic one form, so I mean integrals over closed cycles and also integrals over cycles joining zeros, live in z plus iz, then I can construct the following map from my surface to a torus. The torus would be plane C quotient over z plus iz. So this is a torus which is obtained from identifying opposite sides of a standard square. And the map is as follows. I fix one of the zeros, P1, and then I join any point of the surface P by some curve with P1, and I compute the integral of omega, and I compute it modulo z plus iz. Of course, there are other curves which can be used to join P1 to this point P, and they would provide different integral. But the difference between two integrals is their integral of a closed path, and all closed paths give rise to integrals in z plus iz. And since I quotient over z plus iz, this number modulo z plus iz is well defined. So I constructed a map from my surface to a torus, and one can easily check that this is a ramified cover where all the ramification points are all one and the same point of the torus. Our torus was glued from a square. I pull back this square on the cover and I get a tiling by squares. And a similar story is valid for quadratic differentials. It's just a slight variation of this story. So I really get the square tiled surfaces. And now recall that our problem is to compute sort of the volume of a unit ball or under unit hyperboloid. And our volume is just Lebesgue, naive Lebesgue volume. So how do we compute integrals? We make a small mesh, we count number of points in this small mesh, and then we pass to the limit. It is equivalent to, instead of taking a small mesh in a unit hyperboloid, we can take a unit ball. We can consider a ball of large radius r and consider integer points inside of this unit ball, inside of this ball of radius r. And then we have to use the radius of the ball, or rather divide by radius of the ball to the appropriate power to compute the volume of a unit ball. So here we can do the same thing. So we can compute surfaces which correspond to ball of radius n, and they call that radius in our context, it's this positive homogeneous function. It's nothing but the area of the surface. So ball of radius n in our context, it's the space of all square tile surfaces of area at most n. Since they are tiled with unit squares, that's the number of square tile surfaces tiled with at most n squares. So basically, this is the argument why square tile, the count of square tile surfaces, that's exactly this count of Мэйзура-Вича volume. The power is easily definable here. So, and this is, I'm getting out of time. I started like 5 minutes. Oh, no, I still have several minutes. I was told that I have an hour and a half. And so I still have several minutes. So this is this is the history of advances in computation of Мэйзура-Вича volumes. So I was asked by Alex Askin in about 98 whether I have an idea how to compute Мэйzura-Vich volumes. There is an alternative way using interval exchange transformations and zippered rectangles. It's extremely painful. So at this time I said, no, I have no idea. And then since I was hooked by the question, several months later, I came up with the idea that actually one can compute square tile surfaces. So I worked with integer value closed one forms since sort of childhood. It was the first problem which was suggested to me to Novikov. So for me, it was sort of a natural structure. And Maxim Koncevic showed me how to compute contributions from individual graphs and so on. There, some multiple zeta values appear. And then I was trying to find some way to use these multiple zeta values to compute volumes. It is easy for the first several strata. It is very difficult for the remaining ones. And finally, Askin and Okunkov found alternative approach through representations of symmetric group. And it was really efficient. Well, at least relatively efficient. Then there was, for a long time, there was no much progress. And then recently, Daoui Chen, Martin Müller, Adrien Sauvaget, and also with some involvement of Maxime Kazaryan, De Young, Don Zagier. So they made very serious advance through intersection numbers. So now for volumes of strata of abelian differentials, really, basically all reasonable questions are answered. For quadratic differentials, for the principal stratum, there is relatively efficient way through which I suggested through these intersection numbers and stable graphs, and asymptotics is obtained by Amol Agarwal. There is alternative formula through intersection theory due to Chen, Müller, Sauvaget, but for example, large genus asymptotics for individual strata, this is still a conjecture, still conjectural. So the story is not over for quadratic differentials. So also I hear there's a mention of large genus asymptotics for abelian differentials, which is obtained in parallel by Chen, Müller, Sauvaget, Zagier, and separately by Agarwal by different ways. And also by now there is a formula for strata, for principal stratum of these 7 authors through topological recursion. So but there are plenty of advances. There are still open questions. And so in France, their square tiled surfaces became so popular that you see there is a street which is called the street of small squares. And I dream to rent an apartment at some point in this street and to have square tiled surfaces at my postal address on the envelopes. So thank you. This is all what I wanted to tell for the first lecture, and I managed to get in time. So I'm ready to answer questions.
Yeah, thank you very much, Anton. Will you please return to the previous slide? Why do you put Arana Herrera in brackets?
Because when we proved that we got this, how should I say? We proved that frequencies of square-tiled surfaces are the same as frequencies of multi-curves by comparing formulas. When his scientific advisor heard the theorem, he liked the theorem very much and suggested to Arana Herrera to prove this formula geometrically, which was very natural because Maria Mrzahani constructed a map from the space of quadratic differentials to the space of measured geodesic laminations, and somehow this map should know that these frequencies are the same. It is not an exercise, so one has to work a little bit to go in this geometric way, and he obtained the independent proof of our result in these geometric terms using geometry of this map.
Okay, thanks. Maxim wants to make comments, I believe.
No,
Sure.
I just want to ask a question. So, Anton, at the moment, your story looks like an overview of the known results. And the proofs look like a miracle for a moment. So, I wonder whether you are going to show some details of some particular computations, probably in very specific situation, in some special cases, so that me as a student, as a potential student, could not only to know what's happening in the area, but also to be able to enter the subject.
Mm-hmm. I hope that, let me come back to, oops, was too fast. I showed this table on purpose because this was explicit computation. So.
Yeah, but again, it looks like a kind of ansatz, so we should believe that it works, but you are not going to say anything about the proofs. So what if I would be?
No, then it means that I somehow failed my lecture, because my hope was the following: the conceptual proof of this formula for counting square-tiled surfaces was like this. So I count square-tiled surfaces graph by graph. So I put square-tiled surfaces into different bags, and every bag is indexed by corresponding stable graph. So in genus 2, there are these 6 stable graphs, so I have 6 bags. When I work in the given bag, with the given bag, I am doing the following things. So I want to compute square-tiled surfaces corresponding to this particular stable graph. I'm doing it like this. So for each vertex of the stable graph is represented by a ribbon graph. So I have to recall what is the genus associated to this vertex, which is not written here because here genus is 0, so all vertices correspond to genus 0. So I have to take the corresponding, so everything which is drawn here on this picture is a ribbon graph. And also I have letters B on the sides of these ribbon graphs, which are the length of the boundary components. So I know how to count individual contributions of every layer. I'm claiming that count of square-tiled surfaces corresponding to this stable graph as soon as we know how to count this metric ribbon graphs corresponding to individual layers, become sort of an exercise. Because the only thing which remains to do is to glue cylinders to boundary components. When you glue cylinders, the only thing which you can use is to turn cylinder by 0, by 1, by 2, up to B. And that's why you get this extra product of all B's. And that's the description already of all horizontal counting. And a vertical one resembles enormously this computation for the torus. It's not that much different. So to incorporate vertical parameters, you have to compute now everything for h equal to 1, h equal to 2, up to some bound. And this resembles this computation. So conceptually, this is the proof of well, not even the proof of the formula, but the way to proceed.
Okay, and so is it true that so you refer not to the original integrals of the modular space, but just to counting integer point like in the Norbury theorem?
I'm saying that counting integer points in Norbury theorem helps enormously to count integer points in this space of quadratic differentials.
Okay.
That this is, in a sense, more than 95% of the story.
Mm-hmm.
And I should say that to me, the miracle is why it was not recognized many, many years ago, because we discussed volume computations with Maxim Konцевич already in '98, and we spent some time trying to think how to do it.
Well, Anton, just historical remark that actually these volumes of discrete modular spaces were in my paper with Makin of '93.
Oh, you mean these volume polynomials? You mean these guys?
Yes.
Wow.
It was called discretized modular space. So it was counting of actually integer points.
I see. Leonik, I would be do you have some kind of Xerox copy or whatever? I would be happy to have it, and I would be happy to cite it. I never heard about this.
That's, well, you are not alone. Okay. So it was before, actually.
I see. So you knew this count of metric ribbon graphs?
Yes, sure. And we knew the matrix model. It was, of course, the same matrix model that, but we call it what we called a Conцевич, what we stupidly called Conцевич-Penner matrix model. Stupidly, because neither Conцевич nor Penner had anything to do with it.
Oh, then this is normal. So this is Arnold's principle.
So one more lesson: never call what you did by any other names. Just call it somehow, and then it will be possibly someday called after your name.
No. Following Arnold's principle, something else will be called after your name.
Yes. So we just followed this principle, even before, well, someone else did it. But anyway, so there was this model, right?
I see.
Okay, thanks. More questions, comments?
Excuse me. So there are maybe several separatrix diagrams that correspond to one stable diagram.
Yes. Yes, there are many, and we're putting them in the same bag.
Okay, and at the same time, to one separatrix diagram, there may be several stable diagrams.
No. It depends on what you call separatrix diagram, but if you memorize how you glue cylinders to boundaries, no.
Okay, thank you.
Okay, more questions or comments? Then let's... Da, Mish.
Anton, can you show the previous page?
Previous with respect to this one? This one?
Yeah, well, the page when you computed the number of square graphs. Yeah, no, next one. Next one. Next one. Oh. No, when you computed just the number of square like for torus.
Mm-hmm.
When you have...
Oops, sorry. I will find it. Yes.
Yeah,
this
yeah.
One?
Here it is.
Mm-hmm.
Yeah. I kind of... on the last line to the left, where is this z of b came from? So I kind of confused.
Oh, so zeta of 2, this is sum over of, so this is the following sum. If you take 1 over h squared, where h runs 1, 2, 3, etc., the sum 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc., this is zeta of 2.
Okay, that I understand. Yeah.
I should be missing some.
You have a single variable b taken to the power of 1. So you have b1 to...
okay, it just means... okay, yeah.
Yeah.
Oh, yeah, sorry, yeah.
So,
yeah.
Oh, you mean this thing? It's 1 factorial times zeta of 1 plus 1.
I understand. Yeah. Okay. Yeah, I just thought that b means like multi. Yeah, that's fine.
Okay. Let's thank Anton, and we'll wait till the next week.
Thanks a lot. Thank you for your interest.
Yeah.